So I would try to make it more as simple as possible. So with whatever the best knowledge I have, I would like to, share a few of my experiences and some of the basic fundamental elements of calculus, which is going to be used in machine learning, right? So before I start anything, let me start presenting my screen. Right. So once again, a warm welcome. So with the essence of theoretical knowledge you had gained yesterday, today you'll be wondering why we're directly plunging into the mathematical aspects. Yes, that's the course is all about. But let's not make it more dry as mathematics, typical mathematical class. We'll make it a little more. It's a blend of both theory and the mathematics. Okay, so, in fact, the day would have started with the course on linear algebra and then later the calculus, as the flow goes in that way. But, anyway, due to scheduling issues, we had the calculus first and the linear algebra in the remaining part of the day. Right. So, both of these aspects of mathematics are like, sisters, like in the machine learning arena. So they play a very important role in performing most of the machine learning activities. So the core fundamental of most of the machine learning algorithms stands on the basic elements of the calculus and linear algebra. So let me start with a few. I will just add some of the aspects of linear algebra in between, but in the remaining part of the day, you'll be learning the linear algebra in detail. But let me start with a little bit, and then let us go to the calculus. Okay. So what is linear algebra? So I'll just take 5 minutes to tell you about it. The remaining part of the day, my colleague Dr. Anand, is going to give a very wonderful presentation on that. So as the term says, so we are trying to understand everything in real world as linear combinations. So when I try to say machine learning, so it is trying to mimic the human activities. So the natural activities as understood as beautifully presented by Dr. T.N. Nagbhushan and Dr. Chiranjeev yesterday. So the all the natural, that is what basically we are actually talking about as artificial intelligence. So most of the the natural activities can be broken down into linear combination of certain elements. So, so that is basically is something like if I want to tell you about the growth of a human evolution. So if I want to say that, I'm trying to say how exactly the growth can be explained in the form of linear combination of some data elements. So it's actually over the time I'm trying to describe uh, the summation or integration of those data elements towards a particular direction. So something like if I want to see the growth of a tree, the tree grows vertically upwards, towards the sunlight. So as I understand, there is a linear growth. So if I describe the growth parameters in terms of some data elements, so it is the growth can be described beautifully in the form of linear combinations of all those parameters. Okay, and there are a lot of beautiful operations in linear algebra which can explain us how these linear combinations can be presented, just like dot product, scalar product, okay, and some of all these things. Ultimately, I look at the entire parameter space as a matrix space. in linear algebra. And I would like to see that, at any instance, at any state of existence, I describe the system, the natural system, in the form of a matrix, where every column of a matrix is a vector. Okay, so is a vector in linear algebra. And especially, when I want to describe the dynamics of the growth of the tree, so I cannot, I can only describe the state of the growth of a tree, uh, using a matrix representation or a vector representation in linear algebra. But if I really want to try to look into the how the tree has grown vertically upwards, or towards the light. So if I want to step by step, look at a very minute level and see how it is growing. So I definitely require a tool called calculus. So this is where, I require, I am trying to look at the process of how the linear combinations is going to happen with the help of calculus. Okay, so this is the beginning. With that small intro about the linear algebra, let me take you to the world of calculus. Okay, so I think most of the participants here are from mathematics background, and when it's just a kind of most of you might be knowing many a thing, but whatever the knowledge I have, I would like to share with you, and I hope all of you would appreciate that. Yes, so I think most of you might be knowing that originally it was the calculus was called as infinitesimal calculus. So meaning calculating at miniature level. Okay, so just a second. Right. So we're trying to understand the calculus. Okay. So infinitesimal, the term infinitesimal means I'm trying to understand the calculus at a very smaller, minute level of process, any natural process. Say, I just given you an example of how the tree grows vertically, towards the direction of light. So I try to understand at every microsecond or millisecond, that is where, I'm trying to calculate the growth factor. Okay, so that is what calculus all is a meaning, right? So infinitesimal calculus means, you're trying to calculate everything at a very smaller level, and you are trying to observe. So that's where the calculus comes into picture. So most of the natural systems, as I said, it's a linear combination of very, very smaller data elements. I represent them in the form of a vector, and how these vectors are going to change with respect to a certain variable like time. So how the growth factor of leaves, the growth factor of the other branches of the tree, and many other things, the flower, fruit, and many things, all these are basically the data elements, and I try to understand at every stage, and that is basically the use of calculus, right? Now, what is the meaning? As I said, it is taken from a Latin word called calculi. Interestingly, this means a small pebble, which was originally used in medicine. So this term, the term calculi, I think most of you might be knowing, there is a calculi formation in something like a small stone formation in a kidney or something like that. So this was actually originally taken from the Latin word, which mostly was used in medicine. But interestingly, it has been taken into this the mathematics world. Calculi means, representing a small stone or a small pebble. So As you know, earlier small pebbles were used for calculation and computation. So anything the people used to count and calculate. Okay, so in a smaller level, very step by step procedure, they were trying to understand a pattern of something, some system in the in the natural world, in the form of counting very smaller unit of data elements, and that basically started with counting the pebbles. Okay, so that's basically is the beginning. Now to understand, see, basically it provides us, the calculus provides us with uh, okay, it provides us with a set of tools for characterizing changes in the calculations. So that means, if there are small pebbles arranged like this, so let me give and I'm just taking a very trivial example just to tell you what it is. So now these are all the small pebbles. People started, a man standing here started counting the pebbles from here. Okay, and he wanted to understand how these pebbles are arranged. Okay, so then actually he started characterizing the shape of the pebble arrangement. Okay, so now how do I go about it? You have to collectively cover these things. If I try to look at this, so one by one it tries to cover everything stage by stage. So pebble, every time he calculates three pebbles like this. So you can clearly see how he's moving forward while counting the pebbles step by step. Okay, or I can even call a term called piecewise. I cannot count the whole of these pebbles altogether. I take the pebbles piecewise and try to calculate at every step, right? And trying to characterize the arrangement in the form of the a curve represented here like this. Okay, so this is basically is trying to characterize the changes. So how it is actually changing, the calculation is changing like this. So the pattern in which the pebbles are arranged, it is changing with respect to the time in the x-axis. Okay, so if I call in the x-axis, is moving to a forward and is trying to understand how the arrangement of pebbles are made and trying to understand the pattern he has analyzed. So as he move forward, he tries to understand the pattern which is studied already, and trying to forecast what is there ahead. Okay, and that is basically, it provides us with a set of tools which can help us in understanding the changes in any continuous system. So formally, it's a mathematical study of continuous changes. Very simple. Calculus is a term which is used to understand the continuous changes happening in the system. Okay, now let's come to the vector calculus. How different is the calculus? What is special about vector calculus? So here, characterizing the changes. I am trying to characterize the changes in the natural system. Okay. Uh, in calculations using multiple characteristic pebbles. So now in this case, if I take, say, blue pebbles like this, and I arrange it like this. Now, simultaneously, if I try to understand what is the arrangement of these pebbles. Just looks like a line, right? But simultaneously, if I have one more type of pebble, if I want to know more about the system, so I would also try to count red pebbles together along with the blue pebbles. Okay. So what I mean to say, this arrangement of red pebbles is quite different from the arrangement of blue pebbles. So that means, this whole of this is a box. If I take this as, say, a box or a system you're trying to understand, I'm trying to see how this box is described with the help of blue pebbles. I call it as X, and how it is going to be described in the form of red pebbles, that is Y. So together, I need to go with a common description of the system, which can be describable with these two characteristic pebbles. Okay, and that is where I can try to see what is called as a XY coordinate. So this is X and this is Y. Okay, so this is, I call it as a dimension, one dimension. Okay, this is one dimension and this is second dimension. Okay, so with both the dimension, I'm going to describe the characteristic, the changes happening in piecewise manner. So I try to understand the changes happening piecewise or step by step with minimal step size. Okay, and that is basically is vector calculus. Now at every time, I describe this particular, say if I take one segment of this piecewise representation, say let me take this. Okay, this part, this whole of this, I can represent this as a vector of, say, x1 and y1. Okay, so what is x1? X1 is the number of, or the count or the characteristics of blue pebbles. What is y1? It is the number or the characteristics of red pebbles. Okay, and I see the changes happening in x and y in piecewise manner as the time with respect to a variable called t or time or whatever, which is continuous in its own direction, right? And that is basically is all about trying to understand the dynamics of a system which is represented in the form of a vector, okay, using the calculus. So that's all about is vector calculus. Okay. So with the essence of static representation of a system using linear algebra, we are moving towards understanding the dynamics of the system. So that is basically is a shift from how the vector calculus is going to be useful in understanding the changes happening in the any natural system, right? Okay. So characterization of continuous changes in a particular direction. So this is very important. Using multiple types of pebbles is vector calculus. So what do you mean by a direction here? So taking an example of the tree, the growth of a tree. If I take the tree is growing like this, okay, towards upwards, because you have a sunlight here. Okay, so it's moving upwards because it's towards the light. Now what is that x which is going to influence the growth of a tree is because the leaves actually attract towards the sunlight because of the process called photosynthesis. Okay, the leaves are basically responsible for if I represent the leaves as x, okay, X pebbles in terms, they are actually used for characterizing the leaves. Okay, now this is one direction in which I'm trying to describe or characterize the growth happening in the system. But at the same time, if I take another representation, say y, so y could be, say for example, if there is a ceiling here, a hurdle to the growth. So what will happen? So this hurdle is, I put a hurdle on top of the tree. So the tree would automatically will take a change in the direction like this, and it will grow like this. Okay, so it is growing upwards, but at the same time there is a an opposite pressure, which is hurdle, which is represented by y. Okay, so I need to understand so how this hurdle is represented in y. So what is the value for x, the growth speed of leaves, and the opposition from the topmost thing. So that is basically is a vector. I'm going to describe the state of the current growth of the tree, the current state of the growth of the tree with the help of a vector. And I say that it has got a direction. Now you see that the direction is vertical, but at the same time, physically, if you look at this, the direction is changing like this. But graphically, if I want to illustrate both of them in an XY coordinate system, so it is basically tree grows, say like this, it is growing towards X, it is because as it grows, it moves towards X, but as the Y comes in, it will take towards like this. So more the affinity of X, so it will grow towards the light. As there is a pressure, the growth stops. The growth towards X will stop, will slow down. See, look at this. Now, either I think I will exchange the thing. 1 second. I will exchange X and Y here for understanding. Okay. So this is Y and this is X. So it is growing like this, and so let me change the direction. Okay, so this is growing towards vertically, as it is actually orienting towards, it is getting attracted. Look at this, this is getting attracted towards X as the light moves on, but once the Y increases, the pressure increases, this is where let me understand Y starts here, and immediately the growth, the pace of the growth decreases and it becomes static at some time, and I can describe the entire growth in the form of a curve here, an irregular curve. So because now this starts pulling, the pressure starts pulling towards Y, the second dimension, the growth, the pressure from this direction will reduce. Okay, so I'm trying to understand. See, now this is basically is a continuous representation. So this is plotting a curve like this is all about understanding calculus graphically. So calculus, all of you know it's differentiation and integration, but I can easily make things understand with a graphical representation in this way. So where I can see the characteristic curve which represents the dynamics of the changes. Okay, so I hope it makes sense. Yeah, formally it's a study of dynamics of the system using a function of multiple pebbles. So the pebbles are basically the variables, the one which are used for calculating dimensions or directions. So direction is basically is what is these pulls. These attractions are going to decide the direction of the changes happening in the continuous function. Okay, and these X and Y are represented in the form of a vector, and the changes are represented using linear algebraic representation in the form of a vector here. Okay, fine. So let's try to see some of the good examples of real life examples which we are currently very much bothered and pondering about. So you can see the calculus in real life. So you can clearly see the COVID cases. So I think these graphs are quite familiar to all of you, right, these days. So I have picked up these plots from the world meter COVID-19 count, just to illustrate how the the graph, the coordinate system helps us in understanding the changes, the continuous system happening from the whole of 2020. So you can see this, that active case, the total cases was growing like this from February till January, June, and suddenly from July onwards started surging, and September it was a peak, and now it became stable. So this point where you can see this is the highest steep, highest growth, and this helps us in understanding the period in which where the number of cases basically was too high. Okay, so now what I'm trying to understand graphically here is I'm trying to understand the x direction here and the y. So I can see that y is increasing. Okay, so you remember, go back to the thing, as the y increases, so as the x is moving further, so there's a sudden change in the behavior of this, continuous system. And you cannot characterize this. So ultimately, so if I look at this from the perspective of the growth of a tree, I represent the growth in the form of a function of x and y, f of x and y. It's a growth function. So with respect to x and y, this f of xy can be plotted in the form of a curve here. So similarly, here also, just a second. So I can clearly say this the growth function. This is f of x, and in this case it is not f of xy. No, this is f of x. Okay, so f of x is nothing but y, because x is the input, and you can see how it is changing. So f of x is being characterized. The changes, it is changing. It is not constant. The change is not constant. Okay, if the change is constant from the beginning, it would have been lied in the x direction directly like this. Okay, but the change is, it is varying. The changes are varying here. So it is the variation, trying to understand the variation and trying to analyze the entire system is application of calculus. And you can clearly see there's one more, the active cases. Here also you can see there's a steep hike in the active cases, and suddenly at this point it became static. So you can clearly see this point is pointing to September 18th or something like that, somewhere near to that. And from there onwards, there's a sudden decrease, okay, in the active cases. So now that means the function f of x, in this case x is again the time. So you can clearly see the f of x is suddenly decreasing, and I'm trying to characterize y. Okay, so this is decreasing towards downhill. So this is uphill and this is downhill. So I try to find out where it was actually the changes happened. So in a similar way, the deaths. Okay, fine. So what is this? As I said, to try to understand every minute behavioral aspects of a system, I need to have methods in calculus. The study of characteristics dynamics of a dynamic system is performed either by differentiating or breaking or splitting the characteristic function into a multiple terms. Okay, so if I have f of x like this, so I need to split the f of x, which is represented in the form of some curve like this. Okay, I need to break them or sample them. I think most of you might appreciate what is sampling. So I need to break this into smaller segments and try to understand what changes are happening at every segment. Okay, like this. So I try to see with whatever the changes in x direction, so what is the changes happening in y direction like this. Okay, the vertical direction, and that gives me the the diagonal, the third direction of this triangle, okay, which is also called as an hypotenuse, because this is a right angle triangle. So I'm trying to jump into a little mathematics here. So geometry. So every changes, I can represent it with a change in the x and change in the y, and I call it as delta x, and this is delta y. Okay, and the change can be described with this, the third side, which is the hypotenuse. Okay, so now I call this as the slope. Okay, because now when I call it as a slope, if I represent this as a straight line, so which is a function of mx plus c. Okay, so I need to find out what is this slope, and this slope is basically is what is called as the change of y with respect to x, that is delta y. It's a ratio between delta y and delta x. I'll come into that much more detail later on. So that is one function. So it is trying to split everything into small pieces and trying to understand the characteristics into multiple terms. So these are the independent terms and trying to understand what exactly the changes are happening. Then the another method is the integrating or summing up terms into a characteristic function, the inverse of the differentiation. So I try to combine the piecewise changes together, integrate them, and trying to see the continuity of the changes over a long period. Okay, right. So all of you understand what is integration and what is differentiation. Let us move ahead. Okay. Now, quickly coming to the domain of machine learning. So, how this machine learning is going to be supported with the calculus. So, every machine learning activity represented by a characteristic function, like for example, a prediction and or detection. So, prediction is something like, I forecast, as we just now saw, how the COVID cases are increasing like this. Okay. Now, this is where we are right now. This is January 2021. Okay. Now, what would be the projection if I take a different color? This from here onwards. So, what is the change is going to happen? So, that is all about the projection. I clearly do not know. So, either it can diminish or it may increase like this, or it may be static like this. Okay. So, this is basically a prediction. So, based on the historic data here, so I can always predict the characteristics of this function f of x. Okay. So based on the behavior which you have seen in the past. Okay. So that is what we saw in calculus. This is what is being done in machine learning also. Right. So this is basically the prediction or detection. So you want to detect something which is not seen. Right. Or annotation or description. So I want to describe something like, so you can, if I try to describe some activity, say a person, if I take image processing as an application. So if I look at this shape, the person is walking. Okay. So as I move further, I'm trying to describe the activity of walking in the time delta t. Okay. So let's understand this is time t1 and this is time t2, and I'm trying to see at this time he was walking and at this time he was walking. This is history. Now what is going to happen further is also walking. Now I'm trying to understand. So since he's walking here, so I can describe or annotate the actual activity going on. Okay, so then again it's a function. I'm trying to differentiate the entire function or activity going on with respect to t here and trying to understand what is happening. So that's a difference. Okay, so I try to that's basically is a description. Then modeling and classification. So I try to model an existing system in the form of a function. See, if it is a very huge number of parameters are going to be used to describe a system. Suppose if I want to describe myself, I have n infinite number of parameters to describe my characteristics. So that is x1, x2, or x infinity. Okay. So it's a function of infinite number of parameters. So I need to model it with the help of a polynomial or an approximation function. So model is actually an approximation of real system, right? It is not reality, right? So model is an approximation. So modeling basically means approximation, and further classification. I try to see something, try to categorize certain things. So as if the twins are a mother gives birth to a twin, but initially they look alike, their characteristics are alike, but as they grow with respect to time, if I see the behavior, I can classify them as is elder or is one twin. Out of the twins is first fellow or the second fellow, right? So likewise, I try to classify. So for all
Sir,
these
I
things
have
can
a
be
question.
analyzed using the following mathematical methods involving
Sir,
vector
I have a
calculus.
question.
Okay, and
Sir, can you repeat what is the modeling?
vector calculus in core basically a regression and
Yes, I have a question,
using
sir.
gradient. Okay, so we try to use a method called regression and optimization. Let's try to understand these things quickly in further slides. Likelihood maximization. Likelihood means, it is actually what we are expecting. So we are trying to maximize our expectation. So that is likelihood maximization. Fitting a characteristic function which describes the behavior, and least square approximation, trying to approximate a reality with a model with some least squared error. Okay, that is least square approximation. Then transformation and projections. Okay, so let me take you to the next slide. I don't want to detail it now itself and move slowly. Okay, so for all the machine learning activities, we require what is called as a learning, right? So how do I describe the process of learning? Because for me for a human being, if I want to understand the changes happening, okay, so I try to understand with respect to as I visualize, as I observe in an everyday basis, or over the years, I have observed certain things and I learn. Okay, so my learning can be described like this. So my accuracy of learning. So if I plot accuracy here as a function of say, okay, so this is nx. So I try to the time or whatever. So over the years of my learning. So I try to understand my initial accuracy as I move towards in my years was less, and suddenly I'm increasing my accuracy of learning like this. Okay, so this is called as an accuracy, and this is a function of the years. Okay, so how did I learn? Right, and there's one more plot I can say is my loss. So if I plot my learning loss, how much did I not learn accurately? So over the years, initially my loss was very big, means I was not very accurate, but as I moved towards further, my loss became small. Okay, and this is what we basically call it as a gradient ascent. Okay, this is ascent and this is descent. Okay, and if I look at this characteristic function piecewise, I try to see the slope of every point at every location like this, and I try to see how the changes, and this is where the big leap is. You can see if I sample this, and this is where my learning became more faster. Okay, but I became more accurate at this point. And here my loss became very small. So as I move towards, my loss became very small here. And again, I break this piecewise. I will see if I look at this is the, yeah. So this Y is basically the loss. So we can clearly see as the over the years, as the accuracy increased, it is gradient descent. So what is gradient? Gradient is the slope, is the smooth slope represented by a curve. So that is what is called as a gradient. It's like, coming downhill or climbing uphill, right? Okay. Calculation data distribution. So modeling the distribution using continuous functions. So you can see, when I talk about distribution, most of you might be knowing a typical bell-shaped curve. So this is called as a normal distribution or a Gaussian distribution. Okay. So when you can see this is my mean. Okay. And this is my standard deviation. Okay. So across these two points. So this, I'm trying to describe a distribution of data. Say now, if I try to understand my kind of, if I take X and Y are here, okay, and try to describe certain people, the students who have scored a score of this value, okay, Y value. So I see that there are huge number of people with this peak, and this is a normal distribution because there is a equal deviation from the middle, the mean. Okay, there are equal number of people who are less than the mean and who are greater than the mean. Okay, so mean average score, right? So in that case, I can always say it is normal. So I would like to make every distribution normal, because my calculation would become more easier. So trying to understand the distribution again piecewise is to break them into samples, and again trying to see the slope. Okay, I'm trying to derive the distribution like this. So now we can clearly see the distribution at every point is constant. It is very static. But if I take a distribution which is something different, something like this. Okay, now my mean is somewhere here. So the deviation is quite big. If I take again break these into small parts, and I take the piecewise changes, it's very small in the beginning here on the left hand side of the mean. But whereas here, if I break them into small pieces again, so I have a very huge changes happening at every point. Okay, so at this point it is changing. So this is where again I try to derive the system and try to understand the distribution. Okay, there's something called univariate and multivariate calculus. Now whatever we saw until now is a univariate, because I'm trying to describe a function, a continuous function in the with the help of only one variable. Okay, so let's see how the data distribution analysis can be doable in a single dimension. When I say univariate, it is single dimension. Let's see a video here. Yeah, hello. Am I audible? Hello.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Okay. Sorry, I think there is an issue with this playing videos. So I'll move ahead. So these videos were actually explaining you how the continuity can be modeled with single variable, single dimensional plots. It's just like having so if I want to see these distributions are plotted, so I have to fit a straight line Okay, and this fitting the straight line is again doable with a step-by-step procedure by calculating the distance between the straight line and these points. And the distances between the straight line and these points will give us the error. So the distance, I call it as an error, right? And this error, my objective is to minimize the error, and that is basically is a problem of optimization, trying to fit this function f of x, okay, to perfectly describe or characterize these red dots, right? Okay, so those 3 videos were all about that. Now, basically the intuition about derivatives is, as I said, it is trying to find out the changes in the slope. So if this is x and this is x plus delta x, okay, and this is y and this is y plus delta y. Okay, so I need to look at what is called as a raise over run. So this is the change of y with respect to the change of x. Okay, so the intuition is if I take f of x equal to some 3x, so if I want to derive this, so this will be 3. Mathematically, the derivation of 3x is 3. So the derivative of f of x is 3. How did you arrive at it? Now let's say this is let's assume this value x is equal to, okay, some 2. Okay, if I substitute that, this will be 6 and this will be 3. Now you can clearly see this. If I take x dash, that is delta x, x plus delta x is 2.001. So if I take 2.001, so this will be 6.001 and this will be 3 times of that. Okay, so it will be 003. Okay, so it will increase thrice, right? So it is delta x is 0.003. If I increase, this is 0.001. Okay, so because of that, so it is rise over run, so 0.00301, so will be 3. So this is the derivative. So this is how you calculate the derivations of any continuous function like this. Now, that's what I wanted to explain. So you can clearly see if I explain the speed of some continuous function is like this. So what I do is I derive this by taking the slope at every point. Okay, the slope is nothing but the change between any 2 points. Okay, so this is the slope. Likewise, this is slope. So I try to draw a tangent. The slope is basically a tangent across every point in the group. So when I take the derivative and I plot it again, so I get the second derivative called the acceleration. I further derive, so you know what is the first derivative and second derivative. Second derivative is all about finding, suppose if I take the derivative at this point, that will be a 0. So my function would be somewhere like this. Okay, so at some point it will become 0. So this blue function is the second derivative. Okay, likewise the jerk. So that means when you accelerate, the speed increases. Okay, so the second derivative of the speed is my acceleration. Okay, so you are then finally the third derivation is the jerk. So when you try to increase the speed, there is a jerk, and that is a derivative of this function, the acceleration. That's the third derivative. Okay, so likewise I can keep on trying to find out the further derivatives to identify much more descriptions of the system. Okay, so these are some of the snapshots I've taken from the course of Coursera. So you can clearly see, so the rise over run. So it's basically f of x plus delta x minus f of x. So this is f of x, This is f of delta x. Okay, so okay. So this is the change happening here, and the run is this, the x direction. So it is the ratio between the y and x. You can clearly see the differences. So this I call it as a difference function, and the difference function will gives rise to the derivatives. So how gives rise to derivative? So as the difference function, as I move ahead, so sorry. Yeah, so if I take the limits of these delta x, see, as I take the limit of delta x moving to 0 of this ratio, so immediately if I try to backtrack and see minimize the delta x towards 0, I can see how the changes is happening, and that is my derivative. I can clearly see the derivative of this change of the f of x plus delta x from this position to this position. Okay, so using the limits function, I can easily limiting the ratio to 0, I can get the derivative of the f of x from this point to this point. Okay, right. So moving ahead, there are some more interesting aspects like the sum of the different rules of differentiation. I can take the sum of two derivatives of the functions like this. So d by dx of f of x and g of x is same as this. Now I'm taking slowly into the mathematics. So these are some of the properties. So if I have two different functions and I try to see the derivatives of those two functions can be added together, and I get the same answer. Okay, and there's one more rule called power rule. So if f of x is a of x to the power of b, then the derivative of that with respect to x is deriving x to the b minus 1, right? A b, b you'll take b into x b minus 1. Likewise, product rule is if I multiply two functions f of x and g of x and take the derivative of that, it will be f of x derivative of g of x and g of x derivative of f of x. Okay. Then chain rule, if there are two functions h of p, h is a function over a parameter p, and whereas p itself is a function, output of a function with a parameter of m. So this is called as a chain link. Something like, uh, the father hates son, but still the mother loves son, and so she's a mother, but father loves mother, right? So he listens to the mother. So in that way, the son gets the job done by the father, because it's a chain link, because you cannot directly ask your dad for some favor. So you, through the mother, you can get it done. So it's a relative function, it's a chain function. So as the changes happening here, so the changes means your mother is very much aflame towards the son. Suddenly the father will also be aflame towards the son. So dh by dm, m is your son and h is the father. So the ratio will be the minimal if this is minimal. Okay, so that's a simple example. Then we have multivariate calculus. So we just saw is a univariate calculus. So what is multivariate? N-dimensional data representation. So that means now initially we saw there is a vector representation of x as any object in terms of x and y. Okay. Now this can be this is actually a simple example of a multivariate representation. But now I see if the number of variables are infinite like this xn, so this is a multivariate description. So most of the real world systems are multivariate calculus. So I need to derive, in that case, so my distribution will be based on multiple parameters. So I cannot have a 2D Euclidean representation. So because as the number of parameters increases, my dimension increases to 3 and 4th and 5th and 6th or nth. So I cannot visualize them. So this third dimension, I call it as Z, and this is X, and this is Y. So a point in this space is actually in linear algebra is is a function of f of x, y, and z. Now, how this point moves around these three? So is like this, this point is basically, like there are three birds trying to, catch this fruit, they're trying to pull this, whatever the fruit or whatever, right? Fruit. So it moves towards X, either X or Z or Y. So this is basically is the behavior of this the plot in vector in linear algebra. But if I want to represent the behavior of this dot over the time, okay, so this will give me a curve like this, and this curve is in 3D. So I try to understand the distributions, and the data characterization is in the form of a polynomial represented with the help of the number of variables. Okay, so you can clearly see. So this can be doable. Now, if I want to differentiate, as I said, I want to differentiate piecewise the behavior of the function. So I need to differentiate it with respect to x, with respect to y, and with respect to z. That is df of dx and df of by dy, df by dz. So this is not a complete differential. This should be a partial derivative. df of dx and d by f of d by y and d by f of d by z. This is where the concept of partial differentiation comes into picture. So you can clearly see here, these are the partial differentiations with respect to only x, y, and z. And this is the with respect to a t. I am taking a single with respect to time. I want to see how the function is changing with respect to x, y, and z. So this is 2t and this, and overall this function can be taken. Now this is called as a chain rule. As I said, d by f by d by x and the dx by dt. So there is a link here. Okay, so there's a chain rule I've applied to understand the changes happening in the system with respect to x, y, z. Overall, taking with respect to d. Right. Right. Now, moving further. So there's something called Jacobian. So a vector of multivariate partial derivatives. Now you can clearly see, as I said, in this example, I take the partial derivative of a function of multiple parameters individually. So when I take this the partial derivatives, I want to see the direction in which it is moving. It is neither moving in x or nor y or nor z. It is moving in a direction which is described by this Jacobian vector. So you can clearly see this is called as a contour plot. If I cannot show you the 3D here, this is an image. If I tilt this 90-degree vertical, this bright spot is a peak, and this dark spot is a valley. Okay, the bottommost. And you can clearly see the arrows, you can see small arrows there. They are the partial derivatives of the function which is moving towards the peak. So this is the f of x moving like this towards the peak. So the arrow shows, you can clearly see the arrows are directed towards the peak. So that means you're moving towards the peak. Okay, so that's a peak. So whereas here, you can clearly see the arrows are outwards. And this is a contour plot, this is outwards, because now here the f of x is moving upwards from this point. And this is towards this point. So that is basically is a contour plot. And why it is called as a Jacobian? Jacobian is a description of these partial derivatives in the form of a vector. So the partial derivatives, I can clearly say d by f of d by x, d by f by d by y, and d by f by d by z. So I describe the whole system the changes happening in the whole system at any given junction with the help of a vector representation whose elements are the partial derivatives of that function okay, with respect to every x, y, z. That's basically is a Jacobian. And the beauty is that when we represent the derivatives in the form of a vector, it's pretty easy for me to describe the current state of the system using a linear algebraic representation. So this is basically the chain rule. You can clearly see d by f by d by x and dt by dx. I can just make a dot product of these two vectors. So this, if I have a vector representation, I can easily do a dot product and to get the total derivative of that. Okay. And if I have, suppose if the function is made up of two sub-variables, so d by x by d by u, and if d by u, x is itself is a function of u1 and u2, two variables, then I get a matrix. Okay. So if in this case, this is f of x. F of x gives me a vector, okay, one variable. But if I have x itself as a function, I am now giving you a chain rule here. So x itself is a function of u1 and u2, two parameters. In that case, I'll get a matrix. So when I get matrix and vectors, my operations would become much more simpler by just performing a dot product. Okay. So there's something called Hessian. It's a double derivative. So instead of performing chain rule, I can directly get a double derivative of d x1 with respect to x1. Then further, whatever the result you get for the derivative of x1 will be further derived to get x2. Okay. So like finding the speed, and acceleration and jerk with respect to multiple parameters. Okay, that is Hessian. So you can clearly say that the derivatives can be explained if in terms of d square f by d x square, that is double derivative. If I have one more term, I can say triple derivatives, d f by d x3 cube, like this. So as the number of parameters increases in my thing, my derivatives will also increase. Further, there is something called approximation, as I said, trying to model a real system in an approximate setup. That is using what is called as a Maclaurin series. I think, am I have enough time? Yes. Yeah. So I think I have another 15 minutes. So the Maclaurin series is basically is trying to approximate the behavior of a function piecewise again with the help of the derivatives. Okay. And you can clearly see it's a polynomial function. So I'm trying to describe the behavior of f of x at certain given point here. Okay. Usually what happens, if I just take a first representation with respect to f, so this will be a straight line like this. So I cannot characterize the behavior of the function f of x given a point over the xy, the vector space. Okay. So if I want to characterize the complete behavior of the function, so f of x can be anything at any given over the entire space. So I need to start deriving it, taking every terms. Take the first derivative of the function here, and with the first term x, so I get a blue line here with a slope m. Okay, and that is my gradient. So I'm trying to approximate the function f of x over the point x. So in this case, x is some 0 or whatever, right? I start with the 0 and I try to characterize the function with the help of a green line, which you can see here, okay, with a slope. That too with first derivative. But this approximation is not good enough to describe my process or the functions. I need to be more precise. So I need to go to the next term, that is the double derivative of whatever you have done with x square, the second term. And I get off into this, and that is represented by a parabolic, semi-parabolic curve represented here. And again, that is not accurate. So as I keep moving on, as the number of terms increases, my approximation will also become more near to the accurate stuff, more real to the reality, okay, of f of x. So I'm trying to model f of x, which is this. Okay, this is the actual function with the help of the pink dots at the end. So I'm very quite closer to this. If I add one more term, it will become much more exactly the same function which I'm trying to represent. So this is basically used to model or trying to represent or project or trying to model a function with a series. Okay, so this is basically called as a power series because at every term has an increase in the number of powers. Okay. Sorry. So further, this can be derived like this and simplified to this final form. And this is basically a Maclaurin's series. There's something called Taylor series. So here what we have done is Maclaurin series, I have characterized the function by taking x equals 0. But you can characterize the function f of x, this white line, white curve, given any point x, arbitrary point x. So I can describe the function at any point. It need not be x equal to 0. So that is the beauty of the Taylor series. Okay. So f of p, f dash p of x minus p. This I'm going to, I don't give you the complete derivation, but this is how from starting from the beginning equation of f of 0, as it is a straight line y is equal to mx plus c, I try to substitute the slope to m, and I try to get this equation. Okay, so likewise it increases, and this is my Taylor series is used to approximate a given function at any given point. Okay. Given just a single point, I can easily model or represent an approximate representation of that function as the number of terms increases. Okay. Fine. So with this, we have a least square approximation which directly represents with a straight line. As I said, you can see the fitting a straight line, that video I could not show, but this line is an approximate fit for the distribution shown in this red dots. Okay, and this function line is represented by y is equal to bx plus a. B is the slope, and I try to find out the distance between every dot here between the line, and that is my least squared error. Okay. So the least squared error is basically, because it is a straight line, it is an Euclidean distance. Okay, but if it is a curve, so I need to find out the slope. So my slope would be, I need to take this x and y, and whatever the least square approximation, I can say this is dy by dx. So whatever the distance I am trying to see here, this one is represented by dy by dx, and that is same as this. Okay, so since it is a Euclidean space, 2D space, I can do this. But if it is a n-dimensional space where you cannot visualize anything, it needs to be a partial derivative of multivariate function. Okay, so that's where the calculus comes into the picture, right? So this is actually a cost function, and this basically is the process of linear regression, fitting the perfect model of a function to characterize the distribution. Okay. So likewise, we have a likelihood approximation, which basically is a two-way classification. So you can clearly see I'm trying to classify a particular group of data sets as either a cat or a not cat with a sigmoid function. So my characteristic function is no longer a straight line, it is a sigmoid function. Okay, so it's a curve, it's a S-shaped curve, and I would like to see how this curve need to be modeled in such a way that I get a best fit of this sigmoid curve so that my likelihood error, the error with the very least error, if I have the distributions consolidated here and the other group of distribution which are here. Okay, so my likelihood error, the probability error across these two should be less. Okay, so my deviation, my slope should be very less here. My slope is very less here. Okay, if anything comes here, the slope will become much bigger and the error will be much bigger. Right? So if the slope is very less, there is no error. So I'm exactly fitting the data in right positions, and that is basically is a likelihood approximation. Okay, and that is log likelihood error. And here also I'm trying to find out the same thing with the help of the derivatives. Similarly, the calculus in gradient computation, that is in backpropagation networks. Okay, and you clearly see how what do you mean by this backpropagation neural network? So all of you know what is a neural network, right? So these are the initial input neurons, and you have some hidden neurons here and some output neurons here. So I clearly see the outputs is getting passed, and these are the outputs, and this is my input. Okay, and so at every point I feed forward the input with some weights and bias. Okay, and I get the calculation done at every activation function, and I get some value moved on to this. I see the output, and this output is an approximation. As I said, it's an approximation to the input. So that means there is a loss, as we saw the loss function earlier. So the loss need to be computed with the help of the slope of that loss, and that is with the partial derivation. You can say, because this is a multivariate function, you can see the loss L, which is an output of the output layer here. I take the loss, the change in loss with respect to the change in activation function, and further the change in activation function with the change in the Z function. Okay, so it is nothing but is a core of the neuron, a single neuron. Okay, similarly this changes will be passed backward to this, and again this is computed as a partial. This is a chain rule. You can see there is a chain rule here applied. Finally, what I get is the errors propagated backward to change X. Okay, not X, sorry, the weights and the bias. So I need to calculate the weight and the bias and update those change the weights and bias with the changes propagated backwards. And this is how the gradient computation happens in backpropagation networks. Okay, so just to understand the gradient and derivatives in spaces. So for example, if a space basically is, I represent visually with a 2D space like this, or it can be a 3D space. So the gradient is basically, every function you see is something like the process of learning or modeling a distribution or optimizing an objective function, right? So these things, they proceed in a particular direction like this, and they'll become like this. So I'm just giving a case here. So this is my say an objective function or something like this. So I'm trying to see how this is moving towards. So this basically in artificial intelligence, I call it as a search to an optimization, search for optimal solution. Okay, so search moves here, and it's somewhere at ends here, it becomes stagnant. So the search basically is moving from one point to another dot, and every point of search there is a slope, there is a change happening. So how this search is being described, and as the search ends, you can clearly see the error will be small. There is no zero. So that means the difference between the real target and the actual position where you are is very less. So here usually this distance is the difference between the real target and the search target and your current position is this. It's quite huge, but when it becomes this, so the slope is zero. Okay, you don't have any changes happening. It becomes quite linear like this. So there is no slope at all. So the search will stop here because since there is no difference needed, you can stop the search at some point. So this is in 2D space, x, y. Okay, but as the dimension increases, the search space will also increase, and it will be, for example, if I have a 3D like this, there's one more Z here. Let me represent a plane like this. Okay, so here the search is moving like this, and at the same time it becomes a valley here, it becomes a peak, and like this it will come. So you can clearly see this search is with in terms of x and y. Okay, and as it moves, comes here, goes direct, sorry, this is y actually. So this is x and z. This is the xz plane. Okay, it is moving like this. Suddenly, the search goes downwards towards y direction, and again upwards in the y direction, like this. So I'm trying to show you the 3D in 2D space. I think you can visualize that. So this is how I'm trying to calculate the gradient. Again, how do I calculate the error or the differences in terms of using the differential function with respect to f of x, y, z. Okay. So here it is with respect to xz. Suddenly here it will become the y will come into picture. Okay, and I'm trying to piecewise them, and again y like this. So I need a partial derivatives to see how the progress of this function is going on. The search is happening in the space. Okay, so this is how the beauty of calculus comes into picture when it comes to this. So, for example, if suppose, see in this case, if I want to find out the shortest distance of search, if I take the search algorithm in algorithms greedy method or whatever. So if I want to see what is the shortest distance between this point and this point, so how did you arrive at it? It cannot be an Euclidean distance. Okay, it's not a straight line. It should be. I need to take the distances piecewise. Take the derivatives of this length. Okay, using partial derivatives and add them all together. Something like if I want to measure the distance from my place to, say, the Chamundi temple. Okay, in Mysore, there is a Chamundi hill like this, and I reside here in the town. So if I want to know what is the exact distance between me and the Chamundi hill, it cannot be a straight line, right? It should be a curve like this, and there is a curve can be like this, because of the hilly region. So my distance is always calculated by breaking the the progress in 3 dimensions piecewise, and I try to calculate the slope here and I integrate all of them to get the actual distance. And this space is basically is called as a Riemannian space. This is not actually a Euclidean space. So where I get the distances calculated using what are called as geodesic distances. Okay, geodesic distances. So that's where exactly you see the application of calculus differentiation comes into picture. Projections. Say, for example, I know I'll give a typical example. You're gone to a hair cutting salon. You're sitting here, okay, and the cutting fellow cuts your hair, and you can see your face here, okay. You can only see the front portion of this. What about the behind? There is one more mirror here, which projects the backside of your head, okay, and you can see them projected back to the front mirror like this. And you can clearly see this is my the hair. So how best you are projected if this mirror is orthogonal to this mirror, exactly 90 degrees, okay, orthogonal. I can clearly see the whatever the thing which is not projected here can be projected here. Now I would like to see the derivative, the error difference will be 0 because this is in a different space altogether. Okay, so the understanding of space and projection will be much more in detail by Dr. Anand. So, but I would like to tell you, if suppose there is a mirror, you keep this mirror here, I can only see this portion. Okay, and this is an approximate projection. Approximate projection of your head. Okay, I can only see a side part of the head, and there is a error. It is not actually the reality. Okay, and that projection, if I see here, now I can clearly see this is exactly a 90 degree. Okay, and so I can say in XY coordinate, this is my stuff, and I would like to project it on to say this. So I have a 90 degree thing, and this is my error. So this error is calculated because of this gradient. Okay, so this slope, because of this angle, the angle with which it is being kept from this point. So this angle tells you what is the angle with which the mirror is kept. That gives me the error of projection, and that is again a gradient function, v of fx, d of x. Okay, fine. So I think I gave you a very rough intuition about how derivatives are useful in projection. Computer vision. So as a machine learning case study, so it is a part of my research. So what we did is using active contours for segmenting nucleus of cancerous cell. So if the nucleus are like this, occluded together, we would have to see how the shape of the nucleus is going to play a role in diagnosing the cancer disease. So I have to evolve a contour towards the actual boundary. The boundary would be like this, somewhere irregular like this. So I put a contour in the outwards. It's a kind of a rubber band. So I try to find out the distance between the actual curve and the contour, like this. So I see that these distances will be reduced iteratively. So it keeps moving towards the curve. So as the error, the distance between this is computed by the slope of the the movement of the curve. So you try to piecewise smooth the curve, okay, step by step, and that is where you try to compute this as a partial differential function. The active quantum, it's an integration of the piecewise terms. So thus the every part is projected like this. This part is piecewisely differentiated so that it fits exactly onto the curve like this. None of these will be integrated to see that how this curve evolves towards the boundary to match the exact shape of the system. Okay. And for that, the partial derivatives are going to be very, very useful. Okay, so I think, with this, I'm almost at the time, I think I've covered only a fraction of what the vector calculus is all about, but with a much more knowledge on linear algebra, which will be covered in the next 2 sessions by Dr. Anand. So you have a much more better intuition about how the calculus is going to be useful in understanding the beauty of machine learning and modeling and prediction and optimization and so on and so on. Right. So I think thank you. If there are any questions, I can take up 1 or 2 questions right now. So I thank the Anand for giving me an introduction and giving me opportunity for this. So if there are any questions, I can take it up.
Yeah, for the audience, if there are few questions that we can so sir can ask few questions we can take. Quickly, this 5 minutes will be very important.
Contact me at my mail ID pmshiba@sjc.ac.in. So there are no questions. Thank you. Thank you.
So we wait for
Thank you, Shivamurthy, for a very good presentation. I would request all the participants to give feedback. We have already communicated, and at the end of the day, we will be correcting this feedback. And any suggestions to improve it, is always welcome. We are actually sharing the basic foundations, connecting you to the mathematics. The first attempt actually we are making to make everyone, like mathematics in applying to research. So applied research can be done through innovations through mathematical models. So in this context, there are many participants coming from mathematics background. How they are looking these lectures from applied mathematics point of view. Maybe that will also help them to take topics and research topics, and also collaborate with the faculty from computer science. So we hope that this will create a new dimension in conducting applied research through very good mathematical approaches. So thank you for your patient listening, and the next talk will be from Dr. Anandraj Ulle. So keep waiting till the next sessions. Thank you very much. Shivamurthy, make announcement for the next talk. Dr. PMS? So next session starts at 12. So we'll join again. Keep waiting. Thank you.
Hello.
PMS, make announcement.
Hello.
Next session. Yeah. PMS, please make announcement for the next session. Dr. PMS? Dr. Gayatri speaking, but we are not hearing. So
Sir,
Dr.
when is
Gayatri,
it?
madam, we are hearing you. Yeah. Now we are hearing. Yes, please.
Sir, when is the next session, sir?
Pardon? Yes, please. No, we are not hearing. We are not hearing you. बंद है रहा
going to upper floor, they will be the stairs. The Rajan sir will be there, or some Rajan sir will be there. Just near the fourth floor. You are towards the right. अभी पहले फिर मैं गलती से पिक कर दिया हर चीज डबल डाउन होती है।
गवर्नमेंट ने लिखा भी है मोटे मोटे शब्दों में ऑनलाइन वालों जो ऑनलाइन पैसे दे सकते हैं आप पोस्ट कर सकते हो ऑफलाइन मुझे लगता है ये मॉक कर देंगे 8 से 7
and no that is true. What do you have to know? You are given the labs or you are allocated the room? Which lab number one? These are the labs for Tokyo.